welcome to Academica's Aqua Circular Conference. My name is Glina Kirila. I will be your host for this webinar. Our speaker will be Mr. Filip Velghe, who is an environmental project engineer with over 14 years of experience in anaerobic digestion. His presentation will show some of the highlights of his research in developing a volatile fatty acid platform, and we'll touch upon the technological challenges that lie ahead. This being said, I will give the word to Mr. Velghe. You may start your presentation, please.
Okay, thank you. Can everyone hear me?
I hear you.
Okay, perfect.
Let's hope everybody can hear you.
Okay, thank you. Yeah, please switch to the
Yes.
presentation. Okay. So actually today I wanted to talk to you about 100 million tons. To give you an idea of the size of this, it's 80,000 Olympic swimming pools filled to the brim, or also 13 million garbage trucks that are completely full. And more accurate, it's 100 million ton of urban biowaste and sewage sludge that is produced in the European Union every year. So it's a huge amount of waste that we produce every year. So we have to treat it somehow. So for urban biowaste, it has known a long history throughout the ages, where initially it was just landfilled. Then it went to incineration, where we at least had some energy recovery. Then for the biowaste, we sent to composting, which has been for a long time the state-of-the-art technology and is still used in a lot of countries. Now the most state-of-the-art is anaerobic digestion, where we recover both energy and the nutrients as digestate from it. But in the Volatile project, we wanted to actually take it a step ahead. Same story for wastewater treatment plant sludge in the European Union, which I'm sure most of you will probably know a lot more of than me. But it also has been sent to landfilling, has been sent to incineration, and still is to this day. Incineration is one of the major treatment options. Can be applied in agriculture as a soil improver to recover the nutrients, but also has its disadvantages because of the pathogens that might still be inside, or heavy metal contamination, or chemical contamination. It can be composted and then sent to agriculture. It can be treated in anaerobic digestion to recover some of the energy, and then sent either to incineration or to composting. But again, here in the Volatile project, we wanted to investigate if we can also recover some materials from it. So as I said in the previous presentation, in the Volatile project, we want to go from a linear economy to a circular economy by integrating a volatile fatty acid platform with anaerobic digestion, and use these volatile fatty acids for different types of applications, secondary fermentations, to make novel products out of it. So very brief, it's 21 partners from 9 countries, with Technalia as project coordinator and OWS as the project technical manager. So OWS, maybe one or two slides about the company. We're an SME, founded in 1988 as a spin-off from the University of Ghent. At the moment, we're about 100 employees, with our head office in Ghent. As you can see on the picture, it's in an old industrial setting, so actually it's quite a nice building to be in. We also have some affiliates abroad in the USA, in Germany, and in Japan. And our main activity is still the Dranko technology, which is a vertical dry anaerobic digestion technology for mainly municipal solid waste, but we also do co-digestion of municipal solid waste with the wastewater treatment plant sludge. I will not go into too much detail. You see some of the plants that we've built, which were also partnered, by the way, in the project, to see if we can integrate the VFA platform with our existing plant. So now back to the VFA platform. So although anaerobic digestion is an efficient and proven technology, which is still new installations are being built, and definitely has its main advantages. But in the end, we still produce a relatively low value output, the biogas. It's energy, it's renewable energy, so it definitely has its benefits and its pros. But if you look at the ladder of Lansing from recyclability, it's still quite low on this ladder. It's no material recovery, it's energy recovery, and some nutrients, of course, in the form of compost. And therefore, the VFA platform to us seemed the next level in a sustainable biowaste treatment. As a logical step from composting to anaerobic digestion, now comes the next step to produce a VFA platform. So we can discern 3 steps in this VFA platform. Of course, first you have the production of the volatile fatty acids. There it starts, of course. But you also have extraction of the volatile fatty acids platform, volatile fatty acids, and then finally the conversion of the volatile fatty acids to the target product that you want. So starting with the production, let me first show you a general overview of anaerobic digestion. So we start with urban biowaste, can be municipal solid waste or sewage sludge, which in the hydrolysis are converted to soluble fatty acids, sugars, amino acids. In the second step, the acidogenesis, these soluble macromolecules are further degraded to mainly C3, C6 organic acids. So it's propionic, butyric, valeric, and caproic acid. Roughly 20% goes to acetic acid, and 4% is transferred to hydrogen gas. In the third step, the acetogenesis, the organic acids, the C3, C6 organic acids, are further split up into acetic acid. So more or less 2/3 of the C3, C6 organic acids go to C2, the acetic acid, and 1/3 is converted to hydrogen gas. And then in the final step, the methanogenesis, these acetic acid can be split to form methane and carbon dioxide. But there are also microorganisms that are able to convert the hydrogen gas combined with CO2 to produce the methane. So to go from the anaerobic digestion process to the volatile fatty acid production process, we more or less need to shut down this fourth step, the methane production, so that we end at so that we end up with these C2 to C6 organic acid as the main target products. As if these are not converted to methane, these will build up in the reactor medium and can be extracted later. So before starting with the volatile fatty acid production, we looked at the biogas potential of these different types of biowaste. So just to, as the process is very similar, we thought, and the biogas production is a well-known process, we started by evaluating this, as it would give us a good indication of what to expect. And here we see clearly that wastewater treatment plant sludge has the lowest biogas potential, whereas separately collected food waste had the highest potential, within the household organics separated mechanically or at source or somewhere in between. From this biogas potential, we then developed a modified test protocol in which we inhibited methane production and favorized volatile fatty acid production. As you can see, the VFA potential yield is very similar to the biogas production yield, which is a very good result because there are a lot of information available on biogas production potential of different waste streams, and this can already serve as a good indication of how feasible it will be in a volatile fatty acid platform, because here you see also waste treatment plants sludge has the lowest VFA potential, with the food waste again the highest potential. The type of biowaste, for those who were in the previous meeting, was one of the questions, but the type of biowaste determines very strongly the VFA spectrum. So as you can see, we have different categories of waste. And you see also, although acetic acid is the main component in all of them, but there are some differences amongst them. And an important one to show is the sludge, the wastewater treatment plant sludge, either before or after anaerobic digestion. But here you see that there are a lot of isobutyric and isovaleric acids, which we only find in small amounts in the other waste streams. So it's something that we typically see. There's no really an explanation at this moment why we only see it in these types of waste, but it's important to take into account if we want to use these products for further fermentations. One major thing that we must acknowledge is that, as you could see from this scheme, is that it will be theoretically impossible to recover as much chemical oxygen demand in the form of volatile fatty acids as we would have been able to do in methane. So you see that only 72% of the methane production comes from these acetic acid acids, and 28% comes from hydrogen production. And although there is a very small conversion from hydrogen to acetic acid, this is mostly negligible. So in theory, if we look at methane production and we want to convert the process to volatile fatty acid production, we will only have maximum 70% of the yield we could have as methane. So instead of looking at this as a major disadvantage, we looked at this as an opportunity, because it means that VFA and biogas production could be a perfect combination. So we did some research on this to prepare a pretreatment step. Okay, in this case, we started from urban biowaste. It's separately collected household organics. We pretreated it, where only roughly 1/3 of the total solids from the incoming waste we sent to the volatile fatty acid fermentation, and the remaining 2/3 went to anaerobic digestion. And with this pretreatment, we were able to produce a 50-50 yield, either as volatile fatty acids or as methane. And this is a big advantage because there are a lot of biogas production facilities already treating this urban waste. So it means that there are opportunities to expand these AD plants with the VFA fermentation technology, so they can still use their existing production. It will, of course, only produce half of the biogas that we're producing now, but instead they will also yield a new intermediate platform chemical with a higher value on the market than just the energy production. And part of the energy could also be used to fuel the whole process. So another way of explaining this is if you look at the biogas potential from the pure biowaste as this dark green column, and we compare this with the volatile fatty acid potential that we could obtain from the same biowaste, you see that it's clearly a lot lower. But if we combine it and we optimize it by increasing the VFA yield, we can see that the combined technology will more or less yield the same output as the pure biogas production, but a lot of them is in a higher value market segment as volatile fatty acids. There's still research ongoing, of course, to increase the volatile fatty acid yield, and I will show you a few examples of this here that we performed on sewage sludge. So it was a heat pressure treatment that was performed on this, and you can see we did it on two different samples, which you see here. The left one is untreated with a very, very low VFA potential. But after we treated it, you see a huge increase in the potential. And the same for the second sample, which was already a little bit doing better than the first sample. But still, after the treatment, we got a much higher yield from this treatment. So this is a very promising one, especially for sewage sludge, which is already on the lower range of the volatile fatty acid platform or biogas potential. So this heat pressure treatment is very promising. Okay, not only should we improve the overall yield, but we should also look at the VFA spectrum and see how we could customize this. Because if you're depending on your input, if your input stream is fluctuating throughout the year or throughout the years, also your VFA spectrum will fluctuate, and your market opportunities will be less optimal because for many fermentations, if you want an optimal process, your input should be as constant as possible. So we're doing now focusing our research on how can we steer the spectrum and how can we keep the spectrum as constant as possible despite a fluctuating input stream. So this is quite an important step and challenge that lies ahead of us. Another thing is, suppress methanogens, of course, as this is a parasitic process if you want to produce VFAs. And here we can see for VGF waste, which is a source-separated organics and food waste, methane production, it's relatively low. But if you look at sewage sludge, you see, although there are some samples which only start producing methane after 4 days, but a lot of them also starting from the start. And that is one of the reasons why a lot of these sewage sludge samples only yield a low VFA production, because already from the start, part of these VFAs are parallel converted to methane. So again, we applied this heat and pressure treatment. So you see here the blue and the purple line are without the treatment. So we see one starting after 3 days, the other one starts immediately from the start. But after the heat and pressure treatment, we saw methane production only starting after 8 days. And this is a very important step because for VFA production, the typical residence time is between 4 and 7 days. So if you can, by treating this material, that methane production only starts after 8 days, then in theory, you wouldn't expect any methane production during your VFA production. And that's very important. So this heat pressure treatment looks very promising, especially for sewage sludge, because it both significantly increases the total volatile fatty acid yield by breaking down the structure of the sludge, but it also kills off methanogens to a large part, so that you don't have this parasitic process going on. So of course, heat pressure treatment, it's an energy demanding process. So we also always have to evaluate if the extra yield in volatile fatty acids outweigh the costs for the pre-treatment. But it's something that has to be done individually on each stream. But from the test results that we have done, it looks like the most promising technology to treat this. And it's a treatment that's already, it's not a novel thing. It's already on the market, so it can be implemented quite fast. It's also being used for anaerobic digestion, so the same treatment can also be used for volatile fatty acid production. So this brings us, after the production, we also have to extract it, of course, because unfortunately, unlike anaerobic digestion, where your target product, methane, spontaneously bubbles from your reactor medium, the volatile fatty acids are dissolved in reactor medium. So our partner Tecnalia developed recovery technology for the volatile fatty acids using membrane extraction, and roughly it's actually we have a reactor medium which contains biomass, some undegraded organics, some macromolecules, some salts, and some volatile fatty acids, of course. And by using membranes, you bring these volatile fatty acids to a pure site with all the biomass and degraded organics. The stuff that you don't want in is keeping on one side, the volatile fatty acids are on the other side, and at a higher concentration. So it's done by a cascade process, by microfiltration, ultrafiltration, which remove suspended particles and macromolecules. Then we have a nanofiltration system to remove sugars and divalent salts. And then finally, of course, you have the reverse osmosis, where we remove water so that you end up with a high concentration of these volatile fatty acids. And here you can see some pictures of the membranes that were used, but also of the products. So in these vials, you see that we start from a dark brown rich VFA rich digestate, and the further we go into the filtration step, the purer and the cleaner the product becomes. So in the end, after nanofiltration, you end up with quite some clear liquid. So in the process, we did not only look at reverse osmosis, but we also did some concentration by a rotary evaporator, which, depending on the availability of a cheap heat source, could also be a an interesting technology to concentrate the volatile fatty acids. And yeah, due to the availability in the lab, we use this one to produce the higher concentrations for sending to the partners, so that they could produce some secondary fermentations from it. And yeah, during the project, we produced quite some concentrated VFA media. Let's see. So we have produced the VFAs, we have extracted the volatile fatty acids, but of course, this is not the end of it, because in itself, the volatile fatty acids only have a smaller economic value. You want to do a little bit more out of it through these secondary fermentations. So as already explained in the previous presentation, but I will shortly repeat it for those who didn't attend the previous one. In the Volatile project, we focused on producing biopolyesters. So it's a PHB, polyhydroxy alkanoates. We produce single-cell oils as an alternative to plant and animal oils for use in oleochemistry. And thirdly, we produce the omega-3 fatty acids using heterotrophic algae to be used as a feed or food additive. So bringing us back to our 100 million tons from the start of the presentation, should not only be looked at as a burden to the environment, but we should see it as a valuable resource in the volatile fatty acid platform. And with this 100 million tons, with the current conversion rate that we obtained in the project, we could produce between 7 and 10 million tons of pure volatile fatty acids. And these in turn could be converted to 2 to 4 tons of either polyhydroxyalkanoates, single-cell oils, or omega-3 fatty acids. So if there are any questions, I will be happy to answer them if there's still some time, or you can contact me through my email address or to my mobile phone.
Thank you for your presentation. We are waiting for questions now.
No questions?
No questions yet.
Either was very clear or very comprehensive that no one understood.
I think you were very clear
for
the people who understand what you are dealing with. Very clear. See?
Thank you. Thank you, Angela.
Okay, if there aren't any questions, then I will thank you again for your participation in this
Would
conference.
there be questions later? Don't hesitate to contact me.
Okay, so thank you for now, and we'll see each other at the next webinar. Bye.
Okay, very well. Bye. Thank you.